So as I promised you, I will let's go to the solution to our optimization problems. We had two optimization problems, right? We had the distance minimization formulation and the variance maximization formulation. I will not show you how to reach the solution. I'll tell you what the solution is right now. How to reach the solution, I'll teach you later when we learn optimization, as I promised you. So let's understand what is the solution to this optimization problem. I'll directly go to the solution without explaining you how I reached it. That I'll teach when we learn about constraint optimization. There is a whole chapter for optimization. So we will learn the details there. Right now, let's go to the solution. So let's assume X is my data matrix, right? X is my data matrix with endpoints, 1, 2, 3, 4 endpoints, and D features, 1, 2, 3, so on, D features, F1, F2, F3, Fd. So this is an N cross D matrix, right? So we saw when we learned about covariance that my covariance, and let's just assume that X has been column normalized, column standardized. Okay, just let me erase this and write it properly. So let's assume it has been column standardized. So what is column standardization? It means the mean of each column is 0 and the variance of each column is 1, or standard deviation of each column is 1. Okay, that's what column standardization means. I'm assuming this. I'm assuming that I've already performed the pre-processing here. Okay, I've already performed the pre-processing, and X itself is already column standardized. Then I can write the covariance matrix of X. Okay, the covariance matrix of X. Let's assume S is the covariance matrix. The covariance matrix of X is, let's say, S. Then we saw that X can be written as X transpose X. We saw this when we learned about the covariance matrix, right? Now, S we know is a D cross D dimensional matrix because this is D cross N and this is N cross D, right? We saw this. We also saw the interpretation of this, that the diagonal elements are nothing but variances and the non-diagonal elements are nothing but covariances for each pairs of features, right? And we know that this was square and symmetric matrix. We saw this when we were learning in the previous section, when we were learning about what a covariance matrix is. Now, let's go to the solution to our optimization problem. So if you actually solve these, either this problem or this problem, at the end of the day, what do we want to find? We want to find their U1s. We want to find the direction of U1, isn't it? So let's connect the dots. So some of you might remember these terms called eigenvalues and eigenvectors. Probably you learned this in your high school, in your 11th or 12th grade. Some of you might have learned this in undergrad. So eigenvalues are represented by lambda 1, lambda 2, so on and so forth, lambda d. So, okay, I'll come to it. V1, V2, so on and so forth, Vd. Okay, so let me just connect the dots here. So I have a matrix X, S, which is a square symmetric matrix of size D cross D. Now if I compute the eigenvalues, of S, okay, since it's a D cross D matrix, I will get D eigenvalues. Okay, so I'll tell you the definition of what an eigenvalue is and what an eigenvector is. Okay, and the eigenvectors of S. So for every eigenvalue, there is a corresponding eigenvector. So let's call this V1. The V1 corresponds to lambda 1. V2 corresponds to lambda 2. V3 corresponds to lambda 3. V4 corresponds to this. Similarly, Vd. Okay, these are eigenvectors. Let us also assume that lambda 1 is greater than equal to lambda 2, is greater than equal to lambda 3, greater than equal to lambda 4, greater than equal to lambda d, which means this is my maximal eigenvalue. Okay, so how to compute eigenvalues is very simple. You get a very simple function called eigen in NumPy. I think it's a NumPy, which will give you the eigenvalues and eigenvectors of any given matrix. Okay, so it's very, very straightforward. Now, what is an eigenvalue? How is this matrix S and eigenvalues related? So there's a lot of very interesting eigenvalues are very, very fundamental concepts in linear algebra, which have multiple interpretations, right? So PCA actually arrives at eigenvalues. So the definition of eigenvalue, eigenvector is this. If I'm given a matrix S, if let's say, if there are vectors, so here this is a scalar, just mind me, this is a scalar. Okay, if this is a D cross D matrix, this is a D cross 1 vector, right? This is again a D cross 1 vector. So what it's telling me is if there is a scalar lambda 1 and if there is a vector v1 which satisfies this condition, then if there is a scalar lambda 1 and if there is a D column vector of size D v1 which satisfies this relationship. What is the relationships? Lambda 1 v1 equals to S v1. We are given S, right? Then lambda 1 is called the eigenvalue of S and v1 is called the corresponding eigenvector to S. So v1 is called the eigenvector to S corresponding to lambda 1, corresponding to eigenvalue lambda 1. This is the definition. I'm not going to go into the geometric interpretation of this because that will take us considerable amount of energy. All we need to know is that if I get eigenvalues and eigenvectors, it's very simple. Given any matrix, I can obtain eigenvalues and eigenvectors. It's very, very straightforward in Python. Okay, I will connect the dots for you. Just bear with me. Since we know what an eigenvalue, eigenvector is, probably we learned this. We even computed eigenvalues and eigenvectors in our 11th or 12th grade or even in undergrad. But we never understood what is the use of eigenvalues. Now I'll give you a very interesting interpretation of eigenvectors and eigenvalues. Okay, so you might think that, okay, why did we divert into our covariance matrix and eigenvalues, eigenvectors? I'll connect the dots. Please bear with me. Okay, so there's one more very nice property of eigenvalues and eigenvectors. If lambda 1 and lambda 2 and lambda 3, so on lambda d are my d eigenvector. So for a matrix of size d cross d, I will have d eigenvalues and correspondingly d eigenvectors. Okay, corresponding to each eigenvalue. Now, one nice property of eigenvectors is if you take any two vectors, vi, vj, you could take v1, v2, v2, v3, v1, v3, anything. They're perpendicular to each other. So what is, when two vectors are perpendicular to each other, what does it mean? It means vi transpose vj equals to 0. Because cos 90 is 0, right? Or vi dot product vj equals to 0. That's what it means. Okay. So one of the very nice properties of eigenvectors is that eigenvectors are, every pair of eigenvectors are perpendicular to each other. Okay. We'll see what it means. We'll see the geometric interpretation of this in a while. Okay. Having said this, now the interesting part is this. What is my u1? Because if you look at this optimization problem, what I wanted to find was u1. What happened to my u1? Why did we diverge from our actual problem of finding u1? You can prove using optimization, which I promise we will do later, is u1 is nothing but v1. What is v1? v1 is the eigenvector. v1 is the eigenvector of S. What is S? X transpose X. Okay. Corresponding to the largest eigenvalue. The largest eigenvalue, which is lambda 1. Right? You'll get your u1 very easily. You'll get the direction of maximal variance. So this is maximal variance direction. You will get maximum variance direction by just finding. So let's see what we have to do. Okay. So what you're given is X, okay, which is your whole matrix. First step, column standardize X. Second step, I'm assuming that X is already column standardized. Let me just write it properly. So I'm assuming that column standardization of X is done. If it's not done, please do it. Then I compute my matrix S, which is my covariance matrix, as X transpose X. Third step, compute eigenvalues and vectors of S. Okay, let lambda 1 be the largest eigenvalue, so on and so forth. Since this is a D cross D matrix, I will have D eigenvalues and D eigenvectors corresponding to each eigenvalue. Now, your U1 is nothing but V1. Problem solved. So given a data matrix like this, which is n cross D, by just following the simple 4 steps, okay, and computing this is just one line of Python code, as we will see later. Okay, this is literally one line of Python code, because Python actually gives you all the necessary tools to do this. Okay, your U1 is nothing but V1. Simple, elegant. Why? Why? When we actually solve this optimization problem later, I will prove this to you that U1 is nothing but V1. Your top eigenvector, so it's the eigenvector corresponding to your largest eigenvalue. I'll prove this, I promise. Okay, for now, just take it at face value. Okay, the next question is, what is the geometric interpretation of lambda i's and vi's? What is the geometric interpretation? Let's go and understand this. Okay. Suppose if I have my original data like this is my F1, this is my feature 2. Okay. Let's assume my original data was like this. Okay. Let's assume my original data was like this. Okay. Now comes the interesting part. Now your V1 was U1, which means this direction corresponds to V1. We learned that, so if this is two-dimensional data, right? Your data is two-dimensional, which means your D is 2, which means you will get lambda 1 and lambda 2. Correspondingly, you will get V1 and V2. Okay, if this is V1, we know V1 is perpendicular to V2. Given any pair of eigenvectors, we know they're perpendicular to each other, right? So what is V2? V2 is nothing but this direction. This direction is nothing but V2. Right? So which is perpendicular to V1. So what we exactly did here is we took our data, okay, which was represented with feature 1 and feature 2, and we just rotated the axis. Geometrically speaking, what did we do? We literally rotated this by some theta. We also rotated F2 by the same theta. We rotated our axis such that, our top eigenvector corresponds, or top eigenvector of the covariance matrix of X, okay, corresponds to that direction where the variance is maximal, where the spread is maximal. This is the spread, right? This is the spread, right? And the second one, because there are only 2 of them here, right? This is two-dimensional data, which means there can only be 2 eigenvalues, right? And hence there can only be 2 eigenvectors. So the second eigenvector is literally perpendicular to this. Now imagine what happens if I have 10-dimensional data. Valid question. Imagine if my xi's belong to R10, which means my D equals to 10, which means I'll have 10 eigenvalues and correspondingly 10 eigenvectors, so on and so forth, V10. Now V1 will correspond to the direction with maximal variance. V2 will correspond to the second direction with most variance. See, maximum variance is on V1. The second maximum variance is on V2. The third maximal variance is on V3. The least variance is in the direction of V10. Okay, that's the geometric interpretation of it. So given a 10-dimensional space, I'm literally rotating this space. Of course, I can't draw 10 dimension here. Let's just take 2 dimension here. Okay, and let's assume this is my new transformed axis. What I'm doing is I'm literally rotating my axis, right? I'm literally rotating my axis such that my axes are so well aligned such that my top eigenvector v1 will correspond to that direction which has maximal variance. My v2 will correspond to the second most variance direction. My v3 will correspond to the third most variance direction, and so on and so forth. Now comes the interesting part. What does lambdas mean? What is the interpretation of lambdas? We understood what is the geometric interpretation of vi's, but what about lambda i's? This is interesting. So lambda i's explain us what percentage. So basically, okay, let's look at it like this. Let's sum all lambda i's. Okay, let's assume I get some value. Okay, so let's take this relationship: lambda 1 greater than lambda 2 greater than lambda 3, lambda 4, so on and so forth, greater than lambda d. Okay, so let me sum up all of them. 1 to d. Let me call this. Okay, let's just leave this. Okay. So what lambdas explain is this. Let me explain this geometrically for you. That will make it much simpler. Okay. So imagine if my data was like this, f1 and f2. Okay, let me draw it on a fresh page so that I can draw multiple images here. Okay. Okay. So let's assume this was my f1, f2. Okay. This then, of course, obviously, this will be my v1 and this will be my v2, right? So this is one example. Let's take the second example. Let's assume my second example was like this. My f1 is here, my f2 is here. Let's assume my points are like this. So in the first case, they're perfectly aligned with v1. In the second case, there is some spread, right? So again, in this case, this is my v1 and this is my v2. Because in this direction, there is maximal spread, obviously, right? Now let's take a third example. Let's assume in my third example, I have it like this. The spread is, let's say, slightly more. Okay. Of course, it's not as thin as this. Let's assume it's slightly bulged. Okay. Even here, even in this case, my v1 will be this way. My v2 will be this way. Of course, there is more spread on v2 now. Okay. Let's take the fourth example. Okay. Let's assume in my fourth example, my data was like literally a circle. Okay. Very, very circular data. So if you think of it, this is like a straight line. This is like an ellipse. This is like a wider ellipse. This is literally a circle. In this case, what happens? In this case, my v1 will be this way. My v2 will be this way. Okay, let's see what happens with my lambdas. In this case, my lambda 1, I'm just picking some values here. My lambda 1 will be like 3. My lambda 2 will be like 0. Okay, I'll come back and explain. I'll connect the dots, bear with me. These four examples, these four diagrams should clarify it for us. So this, all the data is on literally a straight line. Here we have an ellipse, a thin ellipse. Here we have a thicker ellipse, right? And here we literally have a circle. Okay, here we'll see typically cases like if lambda 1 equals to 3, we'll see lambda 2 like 1. In this case, probably we'll see lambda 1 equals to 3, lambda 2 equals to 2. In this case, we might see lambda 1 equals to 3, lambda 2 equals to 3. Now you might have understood. So lambdas, so in this case, if lambda 1, so lambda 1 by lambda 1 plus lambda 2, what is it? It is literally 1. This is basically percentage of variance in the data that is already explained. So the ratio of lambda I to sum of lambda i's is percentage of variance explained, or percentage of information that is preserved if I just use lambda 1, if I just use v1. So in this case, if I project all of my data to if I just project all of my data to v1, okay, since my lambda 2 equals to 0, since all of them lie on v1, if I just project all of my data to v1, I'm losing no information at all because there is no spread on v2. We saw that spread is basically one way to spread and information are related ideas, right? In this case, what happens? In this case, my lambda 1 by lambda 1 plus lambda 2 is 3 by 4, which means if I project all of this data, onto V1, okay, and if I were to discard V2, if I want to do 2D to 1D projection, and if I chose V1 as the direction on which I'm projecting, I'm going to conserve, or I'm going to explain, or I'm going to retain 75% of the information content. In this case, my lambda 1 by lambda 1 plus lambda 2 is 3 by 5, 60%. So in this case, if I project all of my data, onto V1, I'm only going to preserve about 60% of the data. Why? Because there is some spread on V2 which I'm missing out. By projecting all the data onto V1, okay, if I want to go from 2D to 1D, by projecting all the data onto V1, since there is considerable spread on this axis also, on my V2 axis, I'm going to lose all of that information. And that is roughly like 40% of the information. In this case, lambda 1 by lambda 1 plus lambda 2 is 0.5, which means if I project my data onto V1, I'm almost losing 50% of the information, right? So lambda gives you a relative scale or relative percentage, or lambda I by summation of lambda I going from 1 to d, tells you what percentage of the variance in your data is explained, right? So literally what lambdas tell you, of course V's tell you the direction where V1 tells you the direction where the variance is maximal, V2 tells you the direction where it is second maximal, V3 and so on and so forth. Lambdas tell you how is this data spread. Is this data spread only on one axis, or is it also spread on other axes, right? If lambda 2 is small, you know that I can just project, I can do 2D to 1D projection very, very efficiently, because after projecting, I don't have any more variance left. So lambda I by sigma lambda I tells me what percentage of variance is retained, or what percentage of variance is explained by just that direction. Okay, so this is the geometric interpretation of eigenvalues and eigenvectors. It's a very, 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 very nice connection. I have learned eigenvalues, eigenvectors since my 11th and 12th grade, but I've never understood it this way till the time I learned machine learning. Okay, so this is the geometric interpretation of eigenvalues and eigenvectors.